Hello students. In this video, we are going to learn about next our statistical part, that is moment generating function. Moment generating function. So in a statistics and probability, we called it is this moment generating function as MGF, right? So whenever you are getting the word MGF, MGF stands for moment generating function in statistics, right? So in this video, we are going to learn what is the main application, right? First, we are going to learn the application of MGF. Secondly, we are going to learn definition of MGF. Third, we are going to learn calculation of mean and variance. Calculation of mean and variance from MGF. It means, suppose you know the MGF, how to get the mean and variance, right? Next, fourthly, we are going to discuss some numerical examples. Numerical examples. After that, we are going to learn what is that? Some properties. Properties of MGF, right? So this is what the outline of this video, whatever we are going to study in this video. So next we start with the application of the MGF, right? So it has two application. MGF, moment generating function. Function means you know what do you mean by function. Uh, so here moment generating function, it has two application. One application is the first one, uniquely characterize uniquely characterize the distribution of random variable. What do you mean by uniquely characterize the distribution of random variable? Means with the help of the MJ, we can find the particular random variable followed by which distribution, right? So in your study, you not at all uh, discussed the some named distribution. Third semester, we are going to discuss some named distribution. But before that, how to identify the particular random variable, say x, is followed by which distribution? In statistics, we have some named distribution. Let's say, for example, binomial, Bernoulli, Poisson, normal. Likewise, we have so many several distributions. With the help of the MGF, we can identify if the random variable x, it has certain MGF, and it followed by which distribution. This is first application. That is what uniquely characterize distribution of the random variable. Second application is to calculate mean and variance, right? It will helpful, right? Yeah, the main application of MGF is to get the first distribution of the random variable. Secondly, to calculate the mean and variances, right? So this is what these are what two applications of MGF. The next will go for the definition of moment generating function, right? So now I'm going to write here the definition. definition of moment generating function, right? For a random variable for a random variable x, the moment generating function, right? Uh, we have a notation actually. The moment generating function is defined as mx of t. It means that moment generating function of x in terms of t. How to pronounce it? Mx of t. What is the meaning? M stands for moment generating function of x in terms of t. This is equal to expected value of e power tx. Right? How we discussed the expected value of x, like in a mathematical expectation, that is expected value of x equal to summation xi into pi or integration x into f of x dx. Like that, here also moment density function is defined as expected value of e power tx, right? For all values of for all values of t, for all values of t. So how to define it mathematically? We have mathematical definition also. Mathematically, mx of t means moment generating function of x in terms of t. We know that by the definition, that is e power tx. This is nothing but summation e power tx into p of x equal to x. So here x can take the values 0 to infinity. When it is for discrete, it is for discrete a random variable. Then we have one more formula, integration minus infinity to infinity e power tx f of x dx. This is for continuous random variables, right? So this is nothing but mathematical definition of moment generating function. Then the notation, right? So we have notation also. Notation is nothing but very simple, right? So usually it is denoted by this one. This is what the notation. This is nothing but what? Moment generating function of moment generating function of x in terms of t. This is what the definition of moment generating function, right? So I hope it's clear. Once we completed application as well as the definition. The third point we'll go for calculation of mean and variance from MGF. MGF means moment generating function, right? We go for next point, that is calculation of mean and variance because you know already the applications of mean and variance, right? We discussed it in our regular classes. Calculation of mean and variance from moment generating function, from moment generating function. So now we are going to discuss calculation of calculation of mean and variance by moment generating function. So here we have two methods, right? So before that, I will tell you one point. Basically, we have to, uh, uh, we have two methods actually, method one and method two, right? To get the mean and variance of movement generating function. Mean and variance of any random variable x by the moment generating function. How means we have one a relation, mm, that is mu r equal to, mu r is nothing but earth moment. Mu r is nothing but earth moment. This is equal to expected value of x power r, right? So if you want to mean means what? Put r equal to 1. Put r equal to 1. This is nothing but expected value of x power 1. This is nothing but expected value of x or mu 1, or it is nothing but mean, right? Then suppose if you put r equal to 2, this is nothing but expected value of x square. This is nothing but what? Mu 2. It is not variance, right? We know that variance equal to expected value of x square minus expected value of x whole square, or variance equal to expected value of x square is mu 2, expected value of x is mu 1 whole square, because it is expected value of x whole square. So this is what the variance formula, and this is what the mean formula, right? So this is what this is variance, and expected value of x equal to mu 1 equal to mean, right? So this is what the theory, what we are going to use in our methods. So now we'll go for first method. First method. Then side by side we'll discuss second method also. Second method, right? First method and second method we are going to discuss. So first we'll go for first method. So here, suppose moment genetic function is denoted by mx of t. We know that. What do we know? Mx of t is nothing but moment generating function of x in terms of t, right? Then to get mu r, right? To get mu r, differentiate. What you have to do? You have to take differentiation, right? Differentiate mx of t. You have to differentiate this moment generating function r times, right? R times. Then put t equal to 0. That is, suppose you want mu r, right? So you consider differentiation r times with respect to the t, right? Of what? Moment generating function. We have to take the differentiation of moment generating function at t equal to 0. Say for example, suppose I want, this is the method, first method. It is a very simple method, right? Differentiation and put t equal to 0. How many times you want, how many times if you want to differentiate means it is equivalent to rth value. It's r times. Say for example, suppose you want mu 1. Mu 1 is nothing but what? Our expected value. This is nothing but what? Mean. How to get mu 1, right? So differentiate with respect to t of mx of t and put t equal to 0. Suppose if you want mu 2, right? So mu 2 is nothing but expected value of x square. Differentiate twice with respect to t, that is nothing but d square divided by dt square of what? mx of t, and put t equal to 0. Suppose you know mu1 and mu2, with the help of our basic formula, with the help of this formula, you can get the mean and variance easily, right? So this is the technique to find out mean and variance by first method, right? Next, we'll go for second method, right? Say if x is random variable, if I need to change the color here. Mhm. Okay. So if x is a random variable, right, with moment generating function, with moment generating function mx of t, right, then mu r is given by, then mu r is given by coefficient of, this is important here, coefficient of t power r divided by r factorial, t power r divided by r factorial in 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 the series of, in the series expansion, in the series expansion of mx of t. What is the meaning of this? Now we'll see, right? So what I wrote here, if x is a random variable with moment generating function mx of t, then if you want to get the mean and variance, for that we have one trick by second method, that is mu r equal to coefficient of t power r divided by r factorial in the expansion of mx of t. It means that what? Right. So now we'll see in detail. See, detailing we can see, we know that by definition, what we have, mx of t means what? We have expected value of e power tx. It means mx of t is nothing but expected value outside. So I will explain this e power tx, how we have e power x formula, right? So here I will write e power x formula first, then you got to know that easily you can get e power x equal to, we know that 1 plus x plus x square by 2 factorial plus x3 by 3 factorial plus and so on, like this only, right? Say for example r means x power r divided by r factorial, like that. This is what e power x formula. Then what we have instead of x, we have e power tx. So it means, so nothing will be changed here. First, as it is 1 remains same. Then instead of x, what we have here? Tx. So it is tx plus, instead of x, what we have? Tx. It means that t square x square divided by 2 factorial plus t cube x cube divided by 3 factorial plus and so on, plus t power r into x power r divided by r factorial. This is what the expansion, right? Then apply expectation inside. This is 1 as it is because we know that expected value of constant is a constant. Then second, t you will take outside expected value of x because x is a random variable, not t. Then here t square divided by 2 factorial into expected value of x square. Then t3 divided by 3 factorial, it is expected value of x cube, and so on up to here t power r divided by r factorial, it is into expected value of x power r. This is what our expansion. And what our this statement or second method is telling, mu r is coefficient of t power r divided by r factorial. It is nothing but what? Here t power 1 divided by 1 factorial, right? So you can write this as 1 into 1 plus t into mu 1 t square by 2 factorial is mu 2 t cube by 3 factorial is mu 3 and so on up to t power r divided by r factorial multiplied by mu r. So here coefficient of whatever we are getting here coefficient, that is what mu 1, its coefficient is mu 2. Like this we can expand, and this is what second method, right? So if you not understand, don't confuse. When we solve the numerical examples, you got to know that easily, right? So this is what the method to get the mean and variances from the MGF. Now we'll go for numerical examples. The first example, find moment generating function. Find moment generating function, comma mean and variance for following probability distribution. That is p of x equal to x equal to e power minus lambda power x divided by x factorial. For all x can take the values 0, 1, 2, 3 and so on, right? So this is the question. I mean, this is the example. Here what they want, here they want MGF of this one as well as mean of this one and the variance of this function, right? So we'll go for solution. What they given? given that x is following certain probability distribution function, right? So that is, that probability distribution function is e power minus lambda power x divided by x factorial, right? For all values of x 0, 1, 2 and so on. Then MGF is given by moment generating function is nothing but what? Mx of t. We know that here x values are discrete or continuous. So obviously it is discrete like 1, 2, 3, so on. So MGF is given by Mx of t. So Mx of t equal to expected value of e power tx. How? By definition, right? This is considering by definition. Then mx of t is nothing but summation because x values are discrete. So summation x value starts from what? 0. And it is so on. So it means it is infinity. Then e power tx into p of x. So mx of t equal to summation expected summation 0 to infinity, right? So e power tx, what is p of x? We have e power minus lambda, lambda power x divided by x factorial. Then mx of t equal to, I will take this e power lambda outside because it is out of the summation side, e power lambda minus lambda. Then summation x running from 0 to infinity e power dx. Then what we have into lambda power x divided by x factorial. Right. So here mx of t equal to, it is e power minus lambda as it is, right? Uh, then what we have to do here? Okay, summation as it is. Then if you observe here, this x is common. So I will take uh, e power t into lambda whole power x, right? Divided by x factorial, right? Then mx of t e power minus lambda as it is. Now I will expand here. See here, we know that which one I wrote that formula e power x. E power x means this expression. Instead of e power x, what we have? Instead of e power x, we have instead of e, we have e power t into lambda, right? It means this expression will be 1 as it is plus, right? So here, second term, instead of x, what we have? Instead of x, what we have here? Lambda into e power t, right? Plus, so lambda into e power t whole square divided by 2 factorial, lambda into e power t whole cube by 3 factorial, plus and so on. This is the expression. Just to check, 1 as it is plus, instead of e, what we have? Lambda into e power t. Then instead of like this, let's go on, right? So here mx of t equal to, right? So this sum is equal, see, e power minus lambda as it is. This sum is equal to e power lambda into e power t, right? So it is a sum. Then mx of t equal to e power minus lambda, e power lambda get cancelled, right? Get cancelled? No, 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 not getting cancelled here. I will take e power minus lambda outside. Then what are the remaining thing? 1 minus e power t, right? So this is what our MGF. This is what our MGF, right? So first one is clear, MGF. Then we go for mean and variance, right? To get mean, first we'll go for mean is nothing but mu1. How I can get the mu1 here? D by dt of mx of t and put t equal to 0, right? So mu1 equal to d by dt of what? E power minus lambda into 1 minus e power t, right? Then differentiate this with respect to what? T. So e power minus lambda as it is outside, right? Then 1 minus e power t multiplied by minus lambda into 1 derivative is 0 minus e power derivative is e power t, right? So mu1 equal to e power minus lambda here as it is, then 1 minus e power t as it is here. multiplied by, I mean this minus lambda multiplied by inside minus lambda into 0. 0 minus minus get cancelled. This will be lambda into e power t. Right. Then what do we have the rule? Put t equal to 0 here. Wherever you have t, put 0. That is mu1 equal to e power minus lambda into 1 minus e power 0 multiplied by lambda into e power 0. That is mu1 equal to, so e power minus lambda into 1 minus e power something, I mean something power 0 itself is nothing but 1 multiplied by lambda into something power 0 is 1. It means that mu1 equal to 0 is there. Again, it will be e power minus into 0 multiplied by lambda. This is nothing but e power 0 multiplied by lambda. This is nothing but lambda. Right. So this is what mean. Next, to get variance, we want mu2. Mu2 equal to, right? This is nothing but what? dt square by, d square by dt square of what? mx of t. Then put t equal to 0. So already here we have this one is mu1, right? Then just to take derivative of this, it is nothing but mu2 is nothing but d by dt of e power minus lambda into 1 minus e power t multiplied by lambda into e power t. Again, there are two terms, u into v rule you can apply here. That is mu2 equal to e power minus lambda into 1 minus e power t. So I will take derivative, uv dash plus vu dash, right? Plus e power minus lambda into 1 minus e power t into e power, lambda into e power t whole square. Then in this equation, put t equal to 0. That is mu2 equal to e power 0, e power minus lambda, 1 minus e power 0 will be 1. Then lambda into e power 0 plus e power minus lambda, 1 minus 1. Then lambda into e power 0 whole square. So mu2 equal to, here lambda will get uh, here plus this is 0, lambda square we can get. This is what? Mu2. But what is the variance? Variance equal to expected value of x square, expected value of x whole square. This is nothing but mu2 minus mu1 whole square. So variance equal to mu2 is lambda plus lambda square minus lambda whole square. This is nothing but lambda. So here variance is also equal to lambda. This is what our mean. Mean as well as variance both are equal in this case. Right. Next, second example will go. Example number 2. A perfect coin. Perfect means unbiased. Both has, it has both head and tail. Right. A perfect coin. A perfect coin is tossed twice. Then find the MGF of number of heads. Number of heads. Hence find the mean and variance. Hence, find the mean and variance. So we'll go for solution of this. When coin is tossed, when coin is tossed twice, when coin is tossed twice, then uh, what is the sample space? Then sample space is this one. So here we may get head and head, head, tail, tail, head, tail, tail. This is our sample space. Now what do we want? MGF of number of heads. Let us assume x equal to number of heads. Right. Then what is the probability distribution of x? Here, how many heads in this case? 0. Right. So x can take the values 0, 1 or 2. So now, if you consider its probability distribution, when x is 0 and when x is 1 and when x is 2. Right, whenever x is 0, probability is 1 by 4 because 1 divided by 4. When x is 1, here 1, here 1 means 2 by 4, that is 1 by 2, here 1 by 4. This is what our distribution. Then how to find out mx of t? We know that mx of t is nothing but expected value of e power tx. This is nothing but summation e power tx into p of x. X can take the values here 0 to 2. So now mx of t equal to consider, I mean, multiplying each probabilities, that is e power t into 0, its p of x is 1 by 4 plus e power t into 1, its probability is 1 by 2 here, plus e power t into 2, its probability is 1 by 4. So mx of t equal to e power 0 is nothing but 1. It is 1 into 1 by 4 plus e power t into 1 by 2 plus e power t into 2 or 2t also we can write. E power 2t into 1 by 4. Right. So mx of t, if I take 4 common, it will be 1 plus 2 into e power t plus it will be e into 2t, right? So this is what MGF, you can more simplify mx of t equal to 1 plus, this is nothing but what? 1 plus e power t whole square divided by 4, right? So this is what the this. Just wait. Okay. So this is nothing but 1 plus e power t whole square divided by 4, right? So this is what our MGF. The next target is to find mean and variance of this same case. Now we'll go for finding mean and variance. So you know that how to find out mean. Mean equal to mu1, and mu1 is nothing but first derivative of mx of t when t equal to 0. Then mu1 equal to derivative of which one? That 1 plus e power t whole square by 4. So 1 by 4 is outside from the derivative. It is a constant. I will take 1 by 4. Then I will apply the derivative here. First 2 into 1 plus e power t. You apply the x power n formula, that is n into x power n minus 1. You treat this as x. So 2 into 1 plus e power t whole power 2 minus 1, that is 1, into derivative of this term, that is 1 derivative is 0, e power t is derivative of e power t is e power t. So mu1 is nothing but 2 1 2 ones are 2 twos are, this is nothing but 1 by 2 uh, 1 plus e power t into e power t. Then put t equal to 0 here. Mu1 equal to 1 by 2 1 plus e power 0 into e power 0. That is mu1 equal to 1 by 2 uh, 1, e power 0 is also 1, right? So mu1 equal to 2 by 2, that is 1. This is nothing but what? Mean. Then to get variance, first we need to find, first we need to find mu2. Mu2 is nothing but what? D square by dt square of mx of t, and put t equal to 0. So mu2 is nothing but d by dt of this first one, 1 by 2 into 1 plus e power t into e power t, right? So here mu2 equal to 1 by 2 as it is, right? Again same, u into v. U is this one, 1 plus e power t, and v is only e power t, right? So apply the u into v formula, that is u v dash, right? If you treat, see, u into v, derivative of uv is nothing but u v dash plus v u dash. Dash is nothing but derivative, right? So u as it is, e power t derivative is e power t, plus, and v as it is, e power t, derivative of u, that is 1 plus, derivative of 1 plus e power t is e power t itself, right? Here put t equal to 0. Then mu2 equal to 1 by 2 1 plus e power 0 e power 0 plus e power 0 e power 0. So mu2 equal to 1 by 2 1 plus 1 into 1 in plus 1 into 1. This is nothing but 1 by 2 into 2 plus 1. This is nothing but 1 by, sorry, 2 by 2, 2 by 2 plus 1, somewhere, no, just a wait. This 1 by 2, this 1 by 2, it is for whole, na? It is for whole. It means it is 3 by 2. Now, variance of x equal to mu2 minus mu1 whole square. This is 3 by 2 minus 1. What is the value of 3 by 2 minus 1? This is equal to uh, 1 by 2. 3 by 2 minus 1 is 1 by 2. So this is the mean and variance for this example. We'll go for next example. Example number 3. Find, same question is same here. Find moment generating function. Find moment generating function and calculate mean and variance for the following distribution f of x equal to lambda into e power minus lambda x. So x is greater than or equal to 0. If you observe here, it is a continuous case. Last case we discussed, last two cases we discussed discrete only. So it is continuous case. In this continuous case, we know the formula of mx of t, that is integration e power tx into f of x dx. So we'll go for solution of this. The given distribution function, the given distribution function is f of x equal to lambda into e power lambda x greater than or equal to 0. Then we have mx of t for continuous case, e power tx. What is the formula for continuous case? That is e power minus infinity to infinity, sorry, integration into infinity minus infinity to infinity e power tx f of x dx. But here x start from 0, that is 0 to infinity e power tx. F of x is lambda into e power minus lambda x dx. So mx of t, what I will do, I will take lambda outside from the integration sign, this lambda outside, then e power tx, then e power minus lambda x dx. So here lambda integration 0 to infinity, this is e power minus sign, I will take common. So next inside is e power minus of lambda minus t dx. So here mx of t lambda into, right, it is nothing but integration of something into x, like integration of minus ax. So its derivative is e power minus ax divided by minus times of a, right? So this is what, like this, integration of e power minus ax equal to e power minus ax divided by minus a. Here a is nothing but lambda minus t, right? So integration is 0 to infinity. So we know by integration rule, first we need to put upper limit, then we'll go for lower limit. So when you put upper limit, that is e power minus lambda into t infinity minus, sorry, or divided by this term. Then e power minus lambda dx into 0 minus of lambda minus t. We know that e power minus infinity is 0. This value is 0. Why? Because we know that e power minus infinity is 0. Right? So this is 0 by minus times of minus lambda of t minus something power 0 is 1 minus times of lambda minus t. So mx of t, what I have to do here? Lambda divided by minus times of lambda minus t. I will take outside. Right? I will take outside. Uh, sorry. It is not like that. Very sorry. The lambda as it is, this value is 0 minus 1 divided by minus times of lambda minus t. So this minus get cancelled. Mx of t will be lambda divided by lambda minus t. This is what our mx of t, right? So then next we are going to find out mean and variance. So here we are using that one more definition. Here mx of t equal to lambda divided by lambda minus t. This is nothing but when I take lambda common, this is nothing but lambda into 1 minus t by lambda. This is nothing but 1 divided by 1 minus t by lambda, right? Or 1 minus t by lambda whole power minus 1, right? Like this. We know that one expansion that I will write here. We know that 1 minus x whole power minus 1 equal to 1 plus x squared plus x cube and so on. It is like same, instead of x what we have here, t divided by lambda. That is nothing but our mx of t is equal to 1 plus, instead of x what we have, t by lambda plus t by lambda whole square plus t by lambda whole cube and so on, like this we have. So here mean is what? We know that mean equal to expected value of x equal to coefficient of t1 divided by 1 factorial, t1 divided by 1 factorial, because we know that coefficient of I mean t power r divided by r factorial is mu r. So it is nothing but here 1 by lambda is there, coefficient of t. This is nothing but 1 by lambda. Then expected value of x square. This is coefficient of t square by 2 factorial, right? So, but here we have only t square, not divided by 2 factorial, right? So its coefficient is like this, 2 factorial divided by lambda squared, right? So maybe you are getting confusion here. I will write separately here, just check. So I want this term here, t by lambda we have, I mean t square by lambda square. But what I want, actually t square by 2 factorial. When we are equal, 2 factorial divided by lambda square equal to t square. So that's I wrote it. Then variance, mu 2 divided by mu 1 whole square. Mu 2 is 2 factorial value is 2 divided by lambda square, 1 by lambda whole square. This is nothing but 2 by lambda whole square minus 1 by lambda whole square, right? This is nothing but when I take 1 divided by lambda outside, 2 minus 1. This is nothing but 1 divided by lambda square. Variance will be 1 divided by lambda square. right? So these are what numerical examples. I will cut this part here only. In next part, we are going to discuss properties of moment generating functions.